Magnetic field mapping of Helmholtz coil. The objective of this experiment are to study the magnetic field around the Helmholtz coil and to study the relationship between the distance between two Helmholtz coils and its magnetic field inhomogeneity. A Helmholtz coil is two identical wires with identical electric current flowing in same direction and arranged symmetrically. It is also formed by a pair of identical thin coils of wires separated by a distance equal to their radius. When current is passed through the pairs of coils, a remarkable uniform magnetic field is produced along the axis of the coils. However, when the current flows in the opposite direction, it will change into anti-Helmholtz mode. In the case of Helmholtz coils, the field points of interest are located in the mid-plane between the two coils. As shown in the equation, the strength of the magnetic field is dependent upon three quantities. First, the current. Second, the number of turns in each coil. And last one, the radius of a coil. The apparatus needed are as follows: power supply, Hall sensor, two coils, Comin 2013, and grid made from graph paper. Before the experiment is started, make sure the Helmholtz coil is arranged according to the direction of the Earth's magnetic field. After the North Pole have been determined, make sure the grid is glued with a sellotape to make sure it is stick in its position. Connect the Comin 2013 to the power supply. Next, connect it to the PC for it to run with NetBeam program. Then, connect the Hall sensor that will be used in this experiment. Make sure the connecting wire is connected correctly in the Helmholtz coil. Insert a small cut box at the center of the Helmholtz coil to make sure it is aligned parallelly. The Hall sensor is put at a point and the magnitude of the magnetic field is measured and recorded for x-axis and y-axis. Do not forget to connect the power supply to the earth. Finally, switch on the power supply. This is the experimental setup diagram for this experiment. After the experiment had been set up, the reading of x-axis and y-axis of each point is taken and recorded. As for the center of the Helmholtz coil, attach the Hall sensor to a pen so that it is easy to take the reading at the center of the Helmholtz coil. Same step is repeated for 300 points as shown. This is the formula that will be needed in the calculation to draw the graph. As a result, we got North Pole pointing to the right and South Pole pointing from the left. Some of the vector directions of Helmholtz magnetic field are not properly aligned and deviate from the original vector. This might be due to the reason that there is some other source of magnetic field affected our measurement, such as magnetic source from digital watch and handphone. Besides that, the value of the magnetic field is some points are not accurate as the winding of both coils are not the same and thus affected the reading of the magnetic field. This is why the vector around the coils deviates from the theoretical. As for the magnetic field of Helmholtz coil by different distance between the two coils, after the reading for magnetic field of Helmholtz coil at x-axis and y-axis are recorded, the 3D graph of magnetic field at the y-axis of Helmholtz coil according to different radius is plotted. The analyzed graph has two peaks, and there is a downward groove between them. This is because the Helmholtz coil is aligned in opposite pole. This arrangement is called anti-Helmholtz coil. The downward groove shows the value of magnetic field cancel out each other. We realized that as the distance between the two coils get far away, the magnetic field get cancelled out is higher. This can be observed through the analyzed graph as the downward groove get more deeper as the distance between coils increase from 0 cm, 1.55 cm, and 3.1 cm. As for the conclusion, the direction of the magnetic field is from North Pole to South Pole. The magnetic field gets cancelled out more when the distance increases.